Okay, so welcome everyone to the next episode of the Coffee Breakdown podcast. Today we have as our guest Teobaldo Luda, who is a postdoc at IPP Garching in Germany, and he's working on integrated modeling, trying to combine predictions of core, pedestal, and scrape-off layer to get like a full tokamak description inside the models. He focuses primarily on the pedestal. So welcome, Teobaldo, to the podcast.
Hello, everyone. Yeah, thanks a lot, Aaron, for inviting me here.
Yeah, so I guess to start, I'm just going to have you maybe briefly explain what we mean by the plasma pedestal, why it's important to include in the modeling and important to predict for the tokamak performance.
Yeah, sure. So, mainly the pedestal is important because it's really improving the confinement of the plasma. In fact, it's called the pedestal because when you look at the, for example, temperature or density profiles in the plasma, the core profiles really look like they are sitting on a pedestal, which is elevating a bit the temperature and the density in the edge. And so, yeah, it's really giving a big boost in the thermal energy and overall in confinement by really increasing a lot the temperature and the density at the edge of the plasma. And this is due to a transport barrier in the edge. So we have this edge transport barrier, which is caused by a reduction of turbulent transport, which makes these steep gradients in this edge region. Yeah, because in the end, like in fusion plasmas, we have really very strong temperature and density gradients over the whole plasma, and so we have turbulent transport all over, and so the fact that in this edge region we have this reduction of the transport is really beneficial and really boosts a lot the confinement properties. And so for basically this means that if you want to build a fusion reactor, you can really reduce the size you need by just going into this regime of this H mode regime, this high confinement mode regime where you have the pedestal, which boosts the confinement.
Okay, yeah, very interesting. So it's sort of a way to, just improve the performance of reactor, like twofold or something like that, with a quick change in the physics.
Yeah,
But
exactly.
but like my understanding as so far is that the underlying mechanism, well, we have some grand idea of how this turbulence suppression happens, but like the underlying mechanisms of how it forms, not just the generation of the H mode pedestal, but then how it sustains itself, is still kind of under development. It's an open question. So I guess
Yeah,
that
exactly.
brings an interesting thing. So how do you get to modeling it when we don't really have a solid theory behind it?
Yeah, exactly. So this is, I think, one of the big challenges that we are facing now, because of course you want to do predictions for a reactor. So if you want to do prediction, first of all for ITER, but especially if you want to do a prediction to design a demo, so a fusion reactor that should be producing electricity from fusion, you need some models that tell you how large the device has to be, how strong the magnetic field and the plasma current have to be in order to get the confinement you want to produce enough energy from fusion, assuming a certain amount of energy that you put as input. So you want to achieve a certain energy gain, right? And for core physics, for the core transport, it's really well understood now. So we really have plenty of models with different fidelity, which give you a pretty good estimate of how your temperature and density, and therefore like the confinement in the core should be. But yeah, for the pedestal, it's really a complicated, a difficult question, because you really need to describe all the phenomena that characterize the pedestal, which is really pushing the boundary of the theory-based model that we have. And so what we do is to come up with some empirical model, for example, for describing the transport in the pedestal. And then we also have some other elements, because the pedestal is basically described by two elements. One is the transport, and the second is the MHD stability. And this is because in the pedestal, you first reduce turbulent transport. You start to develop these very strong gradients. And at some point, these gradients become large enough that they destabilize some magneto-hydrodynamic instabilities. And then you get some edge-localized modes, so ELMs, which limit the evolution of the pedestal and is what ultimately sets your pedestal pressure, temperature, and density. And so you need a combination of these two ingredients. And at the moment, we don't have a theory-based description or codes that can give you an estimate of transport in the pedestal. So what we do is we use some reduced or empirical models, and we combine it with a MHD stability code. And so far, the main use code is IPED, which has a very simple assumption for the pedestal transport, and but works pretty well already. And then when you combine it with the MHD stability code, you can predict the pedestal pressure. And then what I've been doing during my PhD is to develop a more accurate pedestal transport model, which could reproduce with a higher accuracy the pedestal in ASICS upgrade for very many different parameters. And so also the idea was to combine these description of the transport in the pedestal also with a description of the transport in the core. And then also combine it with a MHD stability code, which would tell you the point at which you get the ELM. And so yeah, basically now the most common way to describe, to predict the pedestal is to use an empirical model for the pedestal transport with a theory-based code for the MHD stability.
Okay, I mean that's an interesting development, but it kind of hints to me that there was something missing in this EPED model, or at least the pure theory-based code. Do you have any ideas what it is, or was it just failing to reproduce the pedestals inside Aztec's upgrade, or is it is it a fundamental physics problem, or was it yeah, just noise in the measurements or something like this?
Mm-hmm. Yeah, so for example, this EPED model was developed at General Atomics. So after some analysis on the D3D tokamak. And basically, it's derived from some experimental observation. So basically, they observed that the pedestal width is proportional to beta poloidal at the pedestal top. And this fits pretty well for D3D, and actually also for CMOD works pretty well. But then when you try to apply it to other tokamaks, like for example, ASICS upgrade or also JET, this doesn't really reproduce well the experimental data.
Ah, okay.
This is the main part, the main element, let's say.
And right, so because there was already some kind of, let's say, empirical fitting involved even in the EPED model, then it kind of gives what do you say, more acceptance for redoing the empirical fit, but for Aztecs, right?
Yeah, exactly. Because, for example, they have a proportionality coefficient between the pedestal width and the beta poloidal, which basically is never fixed. And for example, it's very different between D3D and ASDEX or JET. And so
Hmm.
you don't have a general model that does it. They also developed further IPED to calculate this coefficient by looking at some KBM stability, so
Hmm.
related to turbulence. But yeah, also this one doesn't really seem to be um, very accurate, especially for jet.
Right. And that kind of brings another question, right? Because if you have to, let's just say we go with this attempt at doing empirical based uh modeling, then wouldn't you have to retune your model for every machine? It seems to be the case, right? And
Yeah,
then
exactly.
that makes it even harder if you want to take these models and predict, let's say, ITER or demo or something, right? So what can you say about that? Is there some way we can leverage the knowledge we have to make something a bit more generalizable?
Yeah, so what I developed during my PhD is an approach similar to IPED.
Mhm.
So again, it's using another empirical law that seems to describe well the pedestals for different machines. And so far, it seems like it works pretty well for ASDEX, JET, and CMOD.
Hmm.
But of course, there is no guarantee that it also works for ITER and demo because I don't know, you might end up in a different plasma parameter where some other kind of transport physics is regulating the pedestal.
Hmm.
And but now, luckily, there has been a lot of effort with the gyrokinetic simulations in the pedestal, and there are currently also some new PhD students working here in IPP, or there is a group in Austin which is really doing a lot of study on that. And it seems like they are finally starting to get something really interesting.
Hmm.
Basically, they observe that the instabilities that they get from these gyrokinetic codes seems to be consistent with the experimental observation.
Okay.
Yeah, and they are also trying to derive some quasi-linear model for describing the pedestal transport out of these gyrokinetic nonlinear simulations. But yeah, this is still very preliminary, I would say, and yeah, it's if you would have to do gyrokinetic nonlinear simulation to describe the pedestal for a future reactor,
Hmm.
we're also in the same time simulating the core and maybe also the script of layer. Just the computational time you need is the computational resources you need are just too much at the moment to really have a tool that is validated on many different tokamaks and can also be reliably used for predictions. But
Hmm.
yeah, I think we are moving in the right direction. So hopefully in the near future, we will see starting to come up some more reliable models.
Yeah, I mean, that's very interesting. I didn't know about these developments. I knew they were running gyrokinetic models on pedestal conditions, but I didn't realize they got somewhere
Mhm.
promising with it. So that's really cool. And I mean, even once we have a better idea what's the theory behind it, the underlying instability mechanisms, like the turbulent instabilities, um, then you can always, I guess, develop a reduced model or some kind of surrogate to speed up the calculation. But if we don't know where it's coming from, it's probably harder to make a generalizable model, in my opinion.
Yeah,
But
yeah.
okay, but that's very cool. And I guess the question, now that you bring it up with the whole turbulence thing, is that if you can predict the transport well, I mean,
Mhm.
there's still the other half, which is the MHD instability, right?
Right.
So do you, I mean, even if you get the transport characteristics right, it doesn't mean that the MHD limit, let's say, is what we think it is. So
Yeah, that's a good point. So it has always been believed that ideal MHD, linear ideal MHD would be sufficient to describe the pedestal.
hmm,
Uh, like it has been found and observed up to now for most of the experimental pedestals with the standard H modes, let's say. So with the because you have different characterization of the elms you can get, these edge localized modes, and you can also have so you can have situations of where your pedestal is actually limited by linear MHD.
Hmm.
So which is described basically with the peeling ballooning model.
Mm-hmm.
So yes, basically for most of the pedestal, you have that the MHD limit is described by a combination of peeling and ballooning modes, which are either current or pressure driven. But recently has been found, especially on jet, where when you go to high resistivity, so with low temperature in the edge of the plasma and high density, you actually trigger these elms much before than expected from this peeling ballooning model. So, which is described by ideal MHD code.
Hmm.
And the ideal assumption is that you have a resistivity equal to 0. But of course, when you start to have a very strong resistivity, you start to destabilize also some resistive MHD modes.
Hmm.
And so it's important also to describe these physics. But fortunately, there has been some work now which shows that you can, instead of running a linear ideal MHD code, you can run a resistive MHD code like Castor.
Right.
And this actually seems to then recover the experimental observations for the pedestal. And
Hmm.
so this is also very promising. And
Okay.
uh, and the good news is that these codes are still not so computationally expensive, so they can still be run on a uh, yeah daily basis for an integrated framework.
Right. Okay. That's also interesting. Yeah, by switching the MHD, like the nature of the MHD modes that exist in this region, then you can get different pedestal behavior. Do you, I mean, this was just brought up recently, so I may be talking out of nowhere. But there's also something about like having collisional turbulent modes in that regime, which is kind of related to the resistivity. And some people are debating whether or not it's truly resistive MHD or collisional turbulence, which is changing the
Yeah, right.
pedestal characteristics. Do you have anything to comment on that, or is this,
Uh,
too
yeah,
specialized?
I think it's very specialized. Like
Okay.
there has been a lot of research in pedestal transport where it seems that um, like collisionality or eta, so the ratio
Hmm.
between the temperature and density gradient, might really change a lot the nature of the turbulent transport in the pedestal.
Right.
But yeah, I would say that these are a level of sophistication, yeah, which become really important when you start maybe to simulate the transport with gyrokinetic codes. Um, yeah, so far, I would say that this really doesn't change the how the pedestal is now modeled with the empirical transport models. So like with the
Hmm.
EPED or the integrated model that I developed. Um, but yeah, so and together with this, I mean, I think it's an interesting point now also to maybe say that you don't have always the same classic view of the pedestal, let's say, because you can have also different regimes
Hmm.
where you want to mitigate elms. And so this opens up really a zoo of different physics that and instabilities that you can get in the pedestal, because of course the elms are these sudden, very disruptive instabilities which make your pedestal collapse really quickly and therefore drive a lot of power into the diverter. And so also already for ITER, it was discussed that if you have type 1 ELMs, so the largest ELMs that you can have, you really cannot tolerate in ITER so many of these instabilities, because otherwise they would basically melt your diverter.
Okay. Yeah.
And so now they are trying to develop some new scenarios where you either mitigate the ELMs or you completely suppress them. And this is by basically driving additional transport in the pedestal. So let's say a bit limiting the effect of this edge transport barrier by driving some additional transport, which it's not clear yet if it's more just turbulent transport or MHD-driven transport. Can also be a mix or something in between.
Right.
And
Okay.
the idea is that this additional transport would limit the rise of the gradients, so that you don't reach anymore these strong disruptive MHD stability, these edge localized modes, which would cause a lot of damage to your diverter.
Okay, so it's sort of like putting a softer limit away, which is like closer to no gradient than the MHD limit.
Yeah, exactly.
Okay, that's an interesting. So then this comes back down to the modeling question I have about the modeling, and this may be more an opinion, that's fair. Do you think it is important to actually model the whole pedestal dynamic behavior? As in, like when it hits this MHD limit, you actually model the transient of the collapse of the pedestal and the rebuilding. Um, is it important to get to that level? Because I also know currently most people treat like an Elm averaged pedestal in
Yeah,
this.
exactly. I think
Yeah.
you basically have two different levels of sophistication that you can go. Basically, the simplest one is to describe the plasma as like a stationary phase. And this is good enough when you want to describe the plasma confinement, because actually the pedestal is staying for most of the time in this saturated phase just before the um, Helm crash. And so, yeah, I think you just want to go to this higher degree of complexity to describe the time evolution of the pedestal. So describe the recovery phase and the Helm crash phase. If you want to, for example, describe really self-consistently the evolution of the impurities, so the flush out of the impurities to understand if you are getting some impurity accumulation, which then can lead to a radiative collapse or things like this.
If we want to keep this sort of time dependent modeling capability in the integrated models, because there are also, as you mentioned earlier, scenarios where elms don't exist or they're very small. And indeed, that's kind of what we want, because at ITER, they don't want these large type 1 elms, which could damage the reactor. So where do you see the modeling going in that perspective? Or do you think these scenarios can be developed realistically, and how can the modeling help?
Yeah, I think for sure that's the ultimate goal, to be able to arrive at that level of sophistication and to be able to describe all the time dynamics. But yeah, I think we are still pretty far away, because to do this also with these different regimes, you would need to be able to include the physics of this additional transport, which is mitigating the ELMs. So yeah, first you would need to be able to describe the reduction of the turbulent transport in the pedestal. And then on top, also put the physics to describe this additional transport, which is maybe some coupling of turbulence and MHD activities. So yeah, I think this is then computationally be very challenging.
Right.
But yeah, I really hope we will get to that.
Okay. Yeah. And I think that how do you, I guess, in your opinion, how do you see this, you know, this going forward? right? Including pedestal predictions inside integrated modeling. Do you think that it's going to be more theory focused, theory driven? Do you think that's the right way to do things, or is as you've done in your project like a semi-empirical approach more pragmatic?
So yeah, I think these two approaches complement each other because you can learn a lot from the experiment and also you can learn a lot from the theory. So I think it's important to have both. And yeah, probably like also for core transport in the moment um, where the theory is good enough to reproduce the experiment and lead up to a better prediction with different parameters than the empirical models. It's where you really have the breakthrough and you're able to make really reliable predictions which are theory based and can be trusted. So yeah, I think it's good to use these empirical models to really explore as much the possibilities of this kind of integrated modeling that you can do. Also possibly with the combination of a scrape-off layer so that you end up also simulating at the same time the scrape-off layer, so solving the power exhaust with the pedestal stability and I mean, yeah, the pedestal performance and the core performance all at the same time.
Mhm.
And yeah, and on the other hand, you have the theory application, which goes on to give a higher fidelity description of the pedestal. And so it's also interesting now to see these um, global core gyrokinetic codes,
Yeah.
which give you a complete simulation of the core using gyrokinetic codes, and this is really fascinating. And so yeah, I hope in the end we will come with a gigantic code which will be able to simulate the whole plasma.
Yeah, so that's super interesting. I agree with you completely. And also I guess currently in talk up like full plasma modeling, the pedestal region is kind of that missing key, right? Because a lot of people do scrape off layer modeling using a different grid, a different code, and different physics in it, and then core modeling, which is, these two don't typically talk to each other because that region, which is the pedestal, is kind of unknown. So we do need something there. Otherwise, these two will never be able to connect to each other. Um, and so I agree with you there that hopefully more developments go in this way. But maybe now we can speak a bit more about your experience in, you know, trying to develop a model for the pedestals. What, in your opinion, were the largest questions or biggest difficulties in developing the model?
Mhm. Yeah, so I have to say for my project here in IPP for my PhD, I was really lucky that when I arrived, in the end, all the pieces that were needed were there, and
Mm.
just to be, yeah, pick them up and assemble them together and try maybe to come up with a clever way to combine them all together so to get um, yeah, a prediction which was self-consistent with all the different parts. Um, yeah, because you don't on, you not only you need to connect all the different regions with each other, but also for every region. So, for example, for the pedestal, you need to describe, uh, for example, the electron heat transport, the ionic transport, the particle diffusivity, and yeah, I was lucky enough to come up with some assumption that in the end seem to work really reliably,
Hmm.
which is also encouraging because maybe it tells you that in the end things are complicated, but not so much so that you can describe them with some yeah, reduced approximation, let's say.
Right.
But yeah, when you do this, you also realize that you need some So first you had some boundary condition at the core, and then you simulate the pedestal, and then you realize that you need some boundary condition also at the pedestal, because they can also change a lot the outcome of your predictions.
Right.
And so also there, like you realize that you need a reliable enough description of the script of layer. And so what I did so far for the script of layer was to include an analytical model, which basically had inside some scaling factor, which were describing the connection between some engineering parameters to the conditions at the separatrix. But of course, you can do it. I mean, it was working well for ASICS upgrade, but of course, when you go to a different device, you have different divertor geometries.
Hmm.
Lot of things change from one machine to the other. So you cannot hope to get something so simple that is so general for different machines.
Right.
And then you need to move to more sophisticated codes, like maybe Sol PS or something in the middle between a very complicated scape of layer code and an analytical model.
Hmm.
And but still, then again the boundary condition moves somewhere else, because then you need to put, for example, the profiles of the temperature and density at the target.
Hmm.
The, and yeah, so the nice thing of this is that this is also a design parameter, let's say, because you know what is the maximum power load that your divertor can tolerate. So this constrains you with, for example, a temperature and density profile at the target,
Hmm.
and then you can say, okay, given this, reconstruct the whole plasma upward, um, where you only give engineering parameters, so maybe the heating power, the fueling rate, the geometry of the plasma, and yeah, you can get a description of the core, the pedestal, and the script of layer. But yeah, also then once you build a machinery of this type, it becomes a very strongly nonlinear system.
Hmm.
And so yeah, to validate it on many different machines and make sure that everything is behaving as expected, yeah, becomes really complicated. And when you want to study some phenomena, then you really have a lot of things to look at. So yeah, like I think already to up to the development I did for ASICS upgrade was still at a manageable level.
Hmm.
And then when you really want to build something like this for which works, which is validated on many different devices, I think there you really need to put a lot of effort and a lot of people working on that, because otherwise it's really a lot of work for one person.
Yeah, the system becomes so complicated that you can't know all the pieces.
Yeah, exactly.
One person can't know all the
Yeah.
pieces.
So much
Yeah.
physics to take into account.
Yeah, no, but I agree with you. I think that's the whole point of the modeling, is that it eventually moves further and further. The boundary condition gets further and further outwards from the machine until it becomes basically the same knobs that the operator has control over, right? And
Exactly, yes.
but of course, yeah, I also imagine at some level things become more machine dependent than physics dependent, right? Like the location
Mhm.
of your gas valves, or the geometry of your diverter, or the materials you use for your walls, or something like this, right? And so it would be interesting to know if there's some abstraction of those machine dependent choices that we can
Mhm.
put in the model, so that we don't need to, like, it becomes another knob for the
Yeah,
operators to
yeah.
control, right?
Yeah,
Yeah.
yeah, absolutely. Especially when you go to the script of layer description, then
Mm.
you really start to be sensitive to the machine parameters. So exactly the wall material, the diverter configuration, um, yeah, like the space that you have between the plasma and the wall, the pumps, the where the valves are located,
Hmm.
and all these features. So yes, as long as you are simulating the confined plasma and your boundary condition is the separatrix, you are still relatively decoupled from uh, the machine design, let's say.
Right.
But then yeah, when you really go to the scope of layer physics, you are really getting doing a bit this transition also between physics and engineering, where these elements become really important.
Yeah, well, actually, that's an interesting point because it was going to be my next question. Is that it seems from what you described so far, one of the complicated parts of pedestal modeling is the boundary condition, which is the scrape-off layer. And okay, dealing with figuring out what those boundary condition values are is its separate problem completely. But then my question is to you is that do you in your studies have you found that the pedestal physics itself is machine dependent? Like, is there some interplay with locations of gas valves or wall materials or the gap between separatrix and the wall? Do
Mhm.
these factors influence the pedestal physics, like the actual stability of the pedestal in what you
Yeah,
study?
yeah, absolutely. Like
Hmm.
for example, in already the empirical model that I developed um, for the pedestal transport maybe doesn't work already doesn't work between jet carbon and jet ether like wall.
Hmm.
So for sure already there is already a clear indication that just the material of the machine is changing something dramatically.
Right.
Or for example also on jet was also observed that when you with different divertor configuration, so depending on where the strike point is located, so yeah, because you have different configurations where the strike point is hitting a vertical or a horizontal plate, and then the strike point is farther away or closer to the cryopumps, and then already this changes a lot. For example, the separatrix density that you get for a given fueling rate.
Hmm.
And so yeah, exactly. This already an important parameter. Or
Right.
also, if you go from a lower single null to a upper single null plasma, and on the lower divertor you have a nice closed divertor with a cryopump, or on the upper divertor it's open and with no cryopumps, you really see that is making a huge change.
Hmm.
And yeah, and the pedestal sees all of this because you change the separatrix conditions, you change the flux of neutrals that enter into the pedestal, and so they change the ratio between the pedestal top and separatrix density. And all these elements have a strong impact on the MHD stability.
Hmm.
And so yeah, by changing these um conditions of the script of layer, let's say, and the separatrix, you change a lot the pressure that you get at the pedestal, and so also the confinement.
Right. So I think that seems to me that it adds an extra layer, which is the neutrals, right? It's not just the turbulent transport and the MHD that you need to account for. There's also the flux of neutrals coming in from the
Right.
scrape-off layer. And then on top of that, maybe the impurities, as you mentioned with the carbon wall and ether-like wall, has an impact as well. So then you have to include
Yeah.
impurity transport. So I
Yeah,
see
yeah,
it's
exactly.
starting to become very complicated. Yeah.
Yeah, 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 exactly. Yeah, and yeah, to also like this is also then pushing the boundaries of what you can do with the scrape of layer models, because maybe you have yeah you have a seeding of impurities to make more radiation. You have maybe a X-point radiator, which
Mhm.
is also not poloidally symmetric, so it's really localized, maybe close to the X-point. And yeah, then you have to translate this information from the scrape of layer code to a transport code for the core, which is by nature colloidally symmetric. So,
Right.
like, I mean, you have the profiles that are 1D. You don't have 2D profiles. So you
Right.
lose a bit this information, and you have to come up with strategies to couple these things together.
Hmm.
And yeah, and of course, also you need a good description of the neutrals. And yeah, so it start to become really complicated.
Yeah, it's true. And like the more I sit down and think about how all the different components inside an integrated modeling, which is, work I do as well, it becomes a question to myself that is these like we can do reduced models, but is a collection of reduced models equivalent to just doing like the full, as you said, this full gyrokinetic 3D, model, which captures the whole plasma, right?
Yeah, right.
Which one
Yeah,
is the better way to go forward? I honestly have no idea
yeah.
myself.
Okay, let's start again.
Okay.
Okay, yeah. So I think it's really a point, a threshold in complexity, basically. Maybe when up to a point where what you want to describe is not so complex and you don't have so much interactions between all the different components. Probably a coupling of reduced models and simpler models is still fine. But then, yeah, when you want to go really to a very general description, which can describes well different devices and include all the possible physics, then for sure you really need to go to more high fidelity and higher detailed models. I think, yeah, that's maybe at the moment.
Yeah. So it's an interesting point because for if we stick with these reduced models, perhaps they're sufficient to give us the answers we need for, designing scenarios or designing reactors, given the computational power and the physics that we know, and have. But perhaps, moving, if we can accelerate these like holistic models, where it's just like one set of equations for the whole plasma kind of deal. If we can accelerate them to the point where those become feasible, I agree with you. That's probably the way modeling should be going in the future, or at least, we hope we can get there.
Yeah, exactly. Especially, I think depends a bit also, given your computational capabilities, you rely on the combination of models that you can use. So, of course, if you don't have the computational resources to run something very complex and very heavy computationally, then you might just try to see how far you can get with some more simplified and reduced models.
Right. So I agree with you completely. And on that note, I think we're gonna call it time for now. I would like to ask you maybe a final question for people or students who want to get involved in this, very interesting field of plasma modeling, especially now we're breaking, new ground with pedestal physics coupled with scrape off layer and like, full tokamak plasma modeling. Um, do you have some advice for them how to get involved, what to look into?
Yeah, I mean, I think really this is a moment where I see integrated modeling becoming more and more important, especially with the creation of new devices. For example, in Italy, DTT or Spark in the US, or ITER, of course, and JT60. And now for the research plans, um, differently from how it was before, we are really at the stage where we can where I see that there is much more contribution from integrated modelers to these project plans. to really tailor and understand better what can be achieved by the research of a certain machine. So for sure, there's going to be more and more position and for this kind of work, and also more requests. And so yeah, I think one can just try to switch more into these topics. So if somebody is already doing some kind of modeling for one of these specific parts, so for sure one can find teams where they are trying to combine different elements together, and all these teams working on the development of integrated models are always eager to find new codes which can add some more physics, or they can run faster, or they are more reliable. And so I think just getting in touch with the integrated modeling community, there's naturally going to be an interest to exchange information and cooperation in that.
Yeah, so I think that's a good advice to have. I know myself, being involved in the integrated modeling community, would love to hear from anybody and everybody who has an interesting model to put in, and we can work on
Absolutely.
integrating it and seeing what's happening. So good
And
point.
same for me, of course.
Yeah, very good point. Okay, and with that, I'd like to thank you again, Teobaldo, for joining this episode of Coffee Breakdown. We had a
Yeah,
bit
thanks a
of
lot, Aaron.
yeah,
Yeah, it
and
was
thanks for
a really
having the
stimulating discussion.
yes, exactly. And I think that a long time coming as well, since we're both working in the same field, and there's lots of interesting stuff to talk about. Um, and also thanks for having the patience with these technical difficulties. I think people viewing this on YouTube will see the camera chopping a bit. So thanks for sticking in with it.
Yeah, no problem.
Yeah, and for everyone out there listening, thanks for tuning in. We hope you learned something interesting and maybe important for your careers through this conversation. And if anybody's interested in integrated modeling, yeah, both of us are open to contact. So,
Absolutely.
yes, see you in the next episode. Bye.
Bye.